We got a really good start on transcription and translation in class, but I wanted to expand on it a little bit because it felt a little rushed at the end here. So go ahead and just ignore this top part and this for now. I want you to look at this image. I just don't want to have to rewrite that on the board. What is transcription and translation first? Before we can understand what it is, I want to talk about why it's important and what's happening. So we always say DNA controls basically everything. It has all of our genes and it has, everything that we could need to live. However, how is that true? So DNA is made up, obviously, of our double helix and all of these nucleotides. Just in case we forgot, adenine, thymine always pair together. Guanine and cytosine always pair together in DNA. How do these four nucleotides actually code for anything? So that's what transcription and translation is. It's that process of taking DNA, which is a bunch of nucleotides, and turning it into something that actually our body can use. So through the process of transcription and translation, we're taking genes or sections of DNA and turning it into proteins. So that's why you always see from genes to proteins. That's what transcription and translation are. So what I have in this image behind me is you can see we're starting off here with our normal part really over here of DNA. Double helix with our two nucleotide base pairs in the middle. Note that we're going to focus on this top strand, which is going to go from 3' to 5'. So what happens is at this promoter site where we're going, okay, start here, we have an RNA polymerase. RNA polymerase is going to come in here, and it's going to function very similar to helicase, where it's going to split open the DNA so that way we can transcribe it. However, it's going to function a little differently than helicase, where helicase leaves it open, so that way we end up with 2 strands of DNA. It's semi-conservative. Here it closes after, so only, I would say about 15, 20-ish base pairs are separated at a time. So that's the role of RNA polymerase. It's going to come through and split open our DNA. Once that DNA has been split open, from the 3' to the 5' end, we are going to call that the template strand, which is going to also be known as the antisense strand. I think the wording on that is a little confusing, that it's our template and antisense, because you would think that it would be template and sense, but it's not. So it's template and antisense. So just remember that. Once RNA polymerase has split this open, what we're then going to do is go through and make mRNA. That's going to be our transcription process. What happens there is we build from the 5' to the 3' end with the, oh my gosh, what's the word I'm looking for? The complement, the complementary nucleotide. But remember, we're talking about RNA being built, not DNA. If we were building DNA, we would actually be using these same 4 nucleotides, but we're building RNA, so we replace our T with uracil. So that's what's going to be built here when we build our mRNA strands from 5' to 3'. This process is going to sound very similar actually to DNA replication. When we're building our 5' to 3' mRNA, it's actually called elongation, same as DNA. So we get mRNA. This is all happening in the nucleus, mind you. Once we get our mRNA transcribed, that's when we're going to move into the translation process. The translation process is when the mRNA is actually going to exit the nucleus through the nuclear pores and go to our ribosomes. So now, let me show you what this actually looks like as far as our nucleotides. So this is kind of overall what's happening. Remember, antisense strand, starting at the promoter, 3' to 5', mRNA is 5' to 3'. Okay, so now, transcription and translation. you're going to need that chart that I gave you guys in class. It looks like this. You'll need that eventually. I'm going to just go through that top example problem on the back side. I know I went through this in class, but just one more time. So DNA will code for this. Imagine this in that top, or in that image I just drew. This is going to be what's on that top strand, the template strand. Then when we're building our mRNA, we're going to be building using the complementary nucleotide. However, remember, we don't have a T, we have a U instead. So I go through here, and I'm just going to put the opposite, because they're literally, it's opposites here. That's all that's happening. So to go from DNA to mRNA, messenger RNA, we put the opposite. So the opposite of G, let me put it here. A. The opposite of G, I'm going to switch colors. Is C. The opposite of T, well, that's actually U, so the opposite would be A. A, U, C, G, C, G, C. This writing is too big, so I'm getting thrown off here. C, G, C, A, U, A, G. Okay, I just did that quick because it would take me too long. If not, just note that here they are opposites, no T, instead we're replacing U. That goes all the way across. This process is actually called our transcription process. We're just transcribing what's in the DNA. So once we get this all written out, this is our mRNA. mRNA is going to leave the nucleus and go into the cytoplasm to ribosomes. We then are going to need to write down our codons. The first codon that we're going to use, and once again, I kind of talked about this in class, how it's kind of like a secret language where each 3 pairs are going to code for some amino acid. So we need to find something that says, okay, our message is going to start now. So that's always going to be, no matter what, with mRNA, it's always going to be AUG. So you need to go through here and find where it's going to start. Okay, this is CAU, that's not going to work. So I go to the next one, AUG. Okay, that works. Imagine though that this wasn't here, AUG wasn't here, I'm going to keep going through just to show. I would be going, okay, CGC, that doesn't work. GCA, that doesn't work. CAU, that doesn't work. But I notice over here we have AUG again. That's not going to be another start codon unless it has already stopped and then is starting up again. In this case, we can just use this one here. But you're always looking for AUG. So I see AUG, and I'm going to go ahead and write that down here. AUG. And let's draw a little line in between. What you'll see is that there was a C that was not used. For scientists actually still don't know why this happens, but there are nucleotides in the DNA in our genes that are actually not used in the transcription and translation process. They're just like fillers. They're called introns, I believe, and then this is called extrons. But this, we just at this point are going to forget about it. It's not useful, so we're just going to move on to the next part. So I just did AUG. That's our start codon, we know that. But now I'm just going to go, because I have my first codon, I'm going to go in 3s and just bring them down. So my next 3, CGC. My next 3, AUA. I would highly recommend writing down these 3 with the dash in between because it's going to make it a lot easier later on when you're figuring out what those codons actually mean. AUA, UGG, CUG, UAA. Whenever you see, I think it's UAA, UAG, and UGA, always at least look at your chart because those are going to be your stop codons. So when you see U in front, I would at least look at your chart because you probably are going to do extra work if you don't notice that you can stop there. So these are our codons. Now, the next thing on your list are your anticodons. And you probably didn't understand why that was important. And I'm going to show you now. Your anticodons are going to be part of tRNA. And also, I don't know if I mentioned, at this point we are now in the translation process. This was transcription, we're now in translation. Your anticodons are going to be what actually bring that amino acid. So let me get another color. Okay. So, we're starting with AUG. The opposite of AUG, let me bring red here, is UAC. Okay? I'm just going to do my opposites real quick. Alright, we have G, C, G. These are all opposites. U, A, U, A, C, C, G, A, C, and A, U. Yeah. Okay. What happens is that we actually have, for our anticodon, is that's going to be on tRNA. So I'm going to show you this picture here so you can look at it on your own notes. It's this picture. It's going to bring in basically the amino acid. So it will look like this. It's kind of like a little loop, oops, loopy loop. I drew this really poorly. Okay, so what happens is the codons are out here and on our mRNA, okay? So it's this strand, our mRNA. Our anticodons have 3 base pairs on them, literally right on the end here like this. The anticodons are going to come right up to the mRNA here. They're going to put the amino acid in place, and it's going to sit there. Now, the anticodons are going to pair with our codons. So we can just use AUG as what we're looking at on the chart. Okay, the anticodon just pairs with the codon. It then brings the amino acid, it waits for the next amino acid to come, and then this part right here with the anticodon, the tRNA, is going to leave. So what it looks like is, let me see how I want to draw this. AUG, I'm going to find it on my chart here. Let me show you. I find it by going, okay, first base, and the codon is A, so I'm going to go down here. The second base is U, so I'm in this first column, and then G. So AUG, I see that it's MET or start. So I'm going to write down MET. Okay, my next one. I'm looking on my chart. I see CGC is my codon. Okay, so C, G, C is ARG. Okay, so what happens is the tRNA a little bit smaller. The tRNA here that has ARG attached to it is going to come up to the mRNA, bring the ARG with it, and that's why the anticodon is important, because it's attached to this tRNA. These two are going to then connect. At that point, this guy floats away. Okay? So now we have MET with ARG combined. Now I'm going to my next codon, AUA. All right. ILE is what it's bringing. Okay? So now it comes over. Boop, boop. We're connecting to ILE. And then at that point, this tRNA leaves. And it just goes on all the way through until we hit our stop codon. At the end, we have this chain formed. Well, now that chain is a protein because we're made up of several amino acids. So that's why the anticodon is important. It's actually connected right here to the tRNA. I'm going to show you one more time. You'll see in the bottom of that image there, you can see the codon, GAG. You can see the anticodon, CUC, and then at the very top of the tRNA, you see the amino acid attachment site. So what's going to happen is it comes right up here with the anticodon. It leaves this amino acid, whatever it's going to be. The next one's going to come up, and this guy will leave. I'm going to put another link on the website. There's a really great animation that demonstrates this a little bit better than what I can do on the board. So I would highly recommend watching that and finishing up these practice problems that require you to go from DNA to mRNA, which is transcription in the nucleus, and then taking that mRNA and turning it into codons and their respective amino acids, which is our translation process. All right, I hope that helped.